Hello, everyone. Okay, let me test this first. Okay, good. Okay, hello again. My name is Adrian from Purdue University. This is a joint work with Arun Iyengar, Ashish Kundu, and Elisa Bertino. I believe Ashish Kundu is also joining us today. He's from Cisco Research. He probably is in the audience. So we are actually we've been tackling a very practical problem. So we all know that Windows malware is constantly evolving, but how do we build machine learning models that can adapt quickly with very few labeled new samples? That's the question that we've been trying to answer in this work. So imagine that you're building an ML-based model to detect Windows malware. So usually you train it with known malware samples, right? But what happens if the attacker actually develop new malware samples? A model trained using the existing malware samples will struggle to identify those new threats. This is actually one of the core challenges we face in Windows malware detection. Retraining the model with the new data seems like an obvious solution. However, acquiring and labeling enough data set is actually a major bottleneck for this approach. But what if we can be smarter about what type of data we want to label? Active learning actually answers this question by prioritizing valuable samples. Those samples have the biggest impact on the model's performance. The selection, there's many selection methods for selecting those crucial samples, such as the uncertainty sampling, methods utilizing rejection thresholds, and methods using contrastive learning. This method can actually greatly reduce the amount of labeling effort we need in the process. However, still question remains: how can we actually use those new samples to effectively update our model? So there are actually two primary approaches when it comes to updating the model in the past work. The first one is called cold start learning, which involves training a fresh model each time when new labels are introduced. A second strategy is called warm start learning, which continues training an existing model with the new samples. However, neither of those two strategies are optimized for the problem that we're tackling in this work, that is updating the model with very few label samples. Our core idea behind our work is an adaptive model should actually acquire the common characteristic shared by a broad range of malware. This actually allows the model to identify new malware families, even if it doesn't match with the previously seen samples. So we propose a new framework that takes Windows malware binaries as input, and then we actually extract the control flow graphs from malware binaries. In the next step, we actually convert the raw instructions in each basic block of the control flow graphs into feature vectors. We use a pre-trained assembly language model called palm tree for this purpose. Our core contribution is actually the shift adaptation model that learns the common features from the processed control flow graphs. This is actually the first of its kind that applies adversarial domain adaptation with graph neural networks for malware detection. So in the next slides, I'm going to talk a little bit more about our shift adaptation model. So our model actually learns directly from existing and drifted malware samples. This actually allows the model to learn the invariant features that persist across malware variants. So our architecture actually comprises of 3 different neural networks. Many of the architecture might be actually familiar to many of you. So it has a generator, it has a discriminator, and it has a classifier. We also define 2 training tasks with the adversarial training task at the forefront. So the adversarial training task actually leverages a minimax game that ensures the learned representation is independent of the malware's origin. So we did not just propose a new model. In this work, we also critically study the current evaluation methods in previous work. So the leave one out approach is actually a very popular evaluation method in the prior works. This approach, while very popular, has a potential flaw. So it can actually overestimate the accuracy of the model by assuming drift, while it might not actually exist. Similar malware families can actually allow a model to perform pretty well on one malware family, even if it was trained on another. So to solve this problem, in this paper, we also proposed a graph-based clustering approach to generate statistically distinct malware clusters. And in the next slides, I will actually show that using our graph-based clustering approach, we can actually generate better separated malware clusters on a commonly used research data set. Okay, so in these slides, on the left part, we actually visualize one of the mostly used malware detection benchmarks for Windows malware. It's called Big 15. It might be familiar to some of you. So on the left-hand side, we actually visualize the graph feature vectors with respect to the original labels. And on the right graph, you can actually see the visualization of the same graph feature vectors, but with the newly generated cluster labels. So as you can see, our method actually can produce significantly more distinct malware clusters. So in our evaluation, we also actually deploy the leave one out setup. So we choose one malware family as unseen family, and we use the rest of the families as the existing families. We also studied how does the size of the training set of the unseen family impact the performance. So for that reason, we actually tested our approach using 20 to 500 training samples from an unseen family. We compared with several state-of-the-art retraining methods in both settings, one with the original label set and one with a cluster label set that we generated. Our results shows that the domain adaptation methods actually use better performance than the warm start learning method, and the cold start learning method actually produce the lowest outcomes when it comes to the newly drifted samples. Our method also outperforms all the baselines in both settings, and it experienced the smallest accuracy drop of 0.5% on average. So in addition to the control flow graphs, we also wanted to ask the question, so what is the best malware representations we can use when it comes to detecting Windows malware? So specifically, we actually look at the other two very popular malware representations from previous research. One is graph-based representation. The other one is image-based representation. So the content-based representation is actually the features you can extract it directly from assembly code from the Windows binaries. So we evaluated the state-of-the-art detectors designed for each of the representations, but also critically, we also integrated our domain adaptation components into those two representations to access its impact. So our results shows that our adaptation model consistently has the highest accuracy across all feature representations, and combining the adaptation approach with our graph representation actually achieved the best result. So we also tested our approach on the real-world malware dataset. So we collected this dataset from March 2024 to September 2024 on a public available malware repository called Malware Bazaar. So we ensure that we collect at least 81 different malware families from each month for this task. So to actually simulate the real-life deployment of our model, we designed two model update tasks. In the first task, we actually use the data from March, April, May as the existing malware data, and July as the drifted malware samples, and we test the trained model on August data. In the second task, we also use the data from March to May as the existing data, and August as the drifted data, and we test it on the September data. So our approach outperforms all the baselines in this task as well. And the most interesting thing is we also tested the accuracy of a fully supervised setting, and our approach can actually match that accuracy with 5 times reduction in the label effort. In the subsequent experiments, we tested our approach using a benchmark called Malware drift for multifamily classification. So our method improved family-level classification by 9 to 14% over the baselines with just 10 new samples per family. So this was done in a closed-set domain adaptation scenario where the pre-drift and post-drift data, the pre-drift and post-drift malware samples, they all come from exactly the same malware families. So our approach can also be extended to an open domain adaptation scenario where in the post-drift data, we can have new malware families. So our evaluation has shown that our approach can accurately detect those new samples as unknown, preventing them from evading detections. So to summarize, our work addressed the classification of drifting malware and the challenge of adapting model with limited labels. We introduced domain adaptation to train adaptive graph-based malware detectors. Our approach outperforms strong baselines in 3 distinct tasks with increasing complexity. Our approach achieves strong performance on research dataset, on the latest real-world malware dataset, also in a classification of multiple malware families. We also highlight the importance of validating the drift occurrence in research dataset. We show that actually in one of the mostly used Big 15 dataset, the malware from different families, they actually exhibit highly similar characteristics. And if we actually rely on using those family labels for evaluation, it's likely that we are going to overestimate the accuracy of the detector. So thank you so much for listening. Before taking any questions, I would also like to mention that I will be on the job market next year. So I would be very interested to connect regarding the industrial positions. Thank you very much.
Well, they are thinking. Okay, I'll ask one question.
Sure.
So, there's certainly the trade-off in terms of what features you use for malware detection classification. As you mentioned, there are some just use the image or raw bytes, and you're using assembly code and also control flow graph. But when you use assembly code and control flow graph, then first of all, you will spend more time on the disassembly. And the control flow graph may not be that accurate because of the code obfuscation. So can you comment on this trade-off?
Sure. Yeah, that's actually an interesting question. So in the paper, we also list some information about the time you need to process for each of the representations. So it turns out that, as we probably all know, like the image-based representation is most efficient. However, it is actually. Let me actually go back to the other slides. I do have the results. So as you can see in a rows, it's a little small. In the rows of image-based results, you can actually see that. No, not this slide. Sorry. On the graph. So if you on the graph, it's for the graph-based features. I think it's the right table. So basically, for the image-based, if you use the image-based representations. Especially if you use the CoStar training, which basically you train a model from scratch using the image, it actually has the lowest performance. But if you actually turn into what we call fine-tuning or warm start learning, it will actually achieve a better performance that we see. So there is a lot of trade-off between the performance that you want and also what kind of time you're willing to spend on pre-processing those data to extract the features. The content-based features, like I mentioned, we actually extract 965 different features from the assembly code. It is actually most time-consuming representations in terms of extracting the features. But the graph representations is between the two. But also it do have, like as we mentioned before, it do has the overall the best performance compared to the other two. Yeah.
If there's no more questions, then let's thank the speaker again.
All right, thank you very much.